if you don't want to be recorded, keep your camera off and make sure that you ask questions via the chat. So the way that this session is set up, we're going to have, I think, 4 speakers. Unfortunately, I think that Ruchi Chowdhury isn't able to join us for this session for personal reasons. But so the way that it will work is that we will start with a presentation from each of our speakers, from Eleonora, then from Dru, then from Marc, and then from Farhang. They're each going to give you a personal perspective on the on future developments. They each are very expert in their field, and they cover slightly different fields in terms of building simulation. They have slightly different directions that they're taking things in with their research. So hopefully this should be a hugely enriching and interesting discussion from them. What I would ask you to do is, while they're speaking, if you have any questions, can you just put them in the chat? We will have, at the end of each speaker, we'll have 10 minutes for questions specifically on their presentation. And then we will have time at the end, after the last presentation, which will be Farhang's, for a more general discussion that brings, where we can ask questions to more than one panel member. And perhaps the panel members may also, having listened to each other's presentations, you never know, they might have some questions to ask each other as well. And I know I've got lots of things. I've had a sneak preview of Dru's presentation. So I think this is going to be extremely interesting. So without further ado then, I will we'll get started, and I will ask, oh, sorry.
I can't make a host from my end.
Sorry? Oh, you can't? Okay, that's fine. I'll do that in just a second once Eleonora is speaking. So what I would like to do is just to invite Eleonora to kick off with her presentation, to share her screen. And I will just mute myself, and if everybody else could remain muted while Eleonora is speaking, please. Thank you.
Okay, so just let me quickly share this. And would that work? Is it full screen? Yeah. Okay. Thanks for nodding. Right. So yeah, my name is Eleonora Brembilla, and my expertise is in particular on daylighting. So my take on this presentation about future development in building energy simulation will be much more focused on the daylight part, but it touches on other fields as well. So very briefly, to introduce myself, I'm now an assistant professor at TU Delft in the Faculty of Architecture and Department of Architecture, Engineering and Technology. And I started really recently working here. I moved this summer from the UK to here. And in the UK, I was a research associate at Loughborough University, working on weather data for daylight modeling together with CIPSI. Before that, I also did a PhD, also at Loughborough University, and the PhD was focused on the applicability of climate-based daylight modeling, which is a daylight simulation method. So also to give you a quick overview, I don't know how much you know or you don't know. I don't know, yeah, what's the preparation of the different student cohorts. So to give you a brief overview of what daylighting and daylight simulation involve. I would say that it has a lot to do with architectural design to start with, because through daylight analysis, you can assess whether a particular shape, the way the building is massed and oriented, has a big impact on how much daylight you would get inside. And of course, the orientation of windows, the size of window, and all those more detail. So it's really important to have daylight assessment straight at the beginning of the architectural process, but then you can also do more detailed assessment when you go into a later stage of the design and look at the more detail of window and shading devices with daylight simulation, for example. So then you decide what type of window, what type of shading device, whether they would move, or all sorts of different variables, and you can simulate the performance that your building will have thanks to daylight simulation. You can also look at inner visual comfort. So then not only drawing consideration about the shape, the architectural shape itself, but also about the people that will occupy the space will experience it, especially in visual terms. And based on those other analyses and into this general approach from the beginning to the end of the design process, you can also use daylight simulation to set up your control strategies. That goes for both windows and shading. So the more the building gets automated now, the more you can try to get an understanding of how it would work best, whether you want the blinds to be controlled automatically or manually, and when should they close and open, and so on and so forth. So this is a general review of what is common in practice nowadays to do in terms of daylighting. And as for what concerns the future development, so slightly more shifting more towards research and development of future daylight simulation, I try to categorize most developments in terms of the relation with time, the time variable, people variables, and data variables. So all of them are obviously interconnected to each other, but they've been going through quite a rapid evolution in the past decades. So starting with time-related variable, we went from using mainly daylight factor calculations, so just considering one single moment in time when the sky is completely overcast and you just don't consider any variation of that situation. You take this worst case example and you assess the building under that condition. And from that, we moved on onto more complex, but also more realistic analysis that we call climate-based daylight modeling. And with CBDM, we typically look at 1 year of discrete moments, say like hourly moment in time. And so now we look at variable related to time-dependent variable, so related to the sun position, to the weather condition at a specific moment. And we can account for both sky and sun condition at the same time. So that was a huge progress already. But you should notice that I used, I said 1 year of discrete moment, because really the different moment, even if they are consecutive, they don't have any influence on each other. So we don't consider what has happened in the past hour to assess the current hour in this analysis. So one possible future development in daylight could also include assessment and a better understanding of how each moment in time influence the following one. And this would be a more dynamic simulation, something like it's done for thermal analysis, but it wouldn't be focused on the building and on the fabric of the building, but more on the human experiences, because daylight has a lot to do with the way we see things. Otherwise, yeah, it's all about our eyes and what we see, not more than other building simulation fields. And so it would be dependent on the personal light exposure history, how a person experienced this moment, but also how it has experienced previous moments. So that brings me to the relation between daylighting and people. So that is a really strong relationship. So all the units that we use for lighting are actually based on the human sensitivity to light. So it's not something that is completely objective and that characterize a certain physical object, but it's something that characterizes our own eyes, our own perception of the surrounding environment. And this has recently also been put under a lot of discussion because about 20 years ago, the visual effect of light were also coupled. It was discovered that we also have non-visual effects of light. So other cells in our eyes that actually regulate and triggers phenomenon, hormone releases that has to do more with the way we regulate our body, for example, to go to sleep or to wake up. So nothing to do with the way we see things, but more the way we, our body works. And so that brought up all new set of research questions, all new set of design possibilities as well. And now there are discussions about whether we should take into consideration all of the different sensitivity of each of our cells in our eyes, and whether we should account for each of these with different weighting depending on the application, but consider all of them while we design things and while we measure things, even in lighting. So that, I don't know how that will develop. It's, in my opinion, is more related to the medical discoveries than the what we can strictly do in architecture or design. But it will be really disruptive for all the fields related to lighting. And it will also need a whole lot of data. So that is also something that is creating a lot of discussion and a big fast-paced evolution in terms of simulation in general and in daylight simulation as well. So we are adding more and more data from our environment into the simulation models. So it used to be mainly focused on geometrical and optical data, which we needed already for the daylight factor. But then on top of that, we added weather data. So for climate-based daylight modeling, we also added all sorts of new models built on weather data and solar radiation models and general climatology studies. And on top of that, because now we have the possibility of relating the simulation, daylight simulation to time and people, as we said, we also added, we can also add now all kind of different data about the relationship between occupants and the built environment, and also the relationship between daylight and other environmental data. So this wealth of data that we can now collect makes for a very, very interesting addition. And the ones I'm more interested in is the research about the operational daylight performance. So what is actually the levels of daylight that we have in the space, not just the simulated one, but how it is in reality, and then how we can improve simulation based on what we record in real spaces. And yeah, it goes without saying that all these new elements, all this evolution brings a higher, just a larger level of complexity with it. And so to handle this complexity, I feel very strongly about the need for good and solid regulations together with the simulations, and also a strong collaboration between different fields. So I think that both regulation and collaboration, the way we create them, should also evolve together with the complexity. So to enable this complexity and this analysis to go further, there should be a whole infrastructure that support this development. So I'm really keen on promoting like the evolution also of regulation, not just of the simulation analysis. And I just give you an example on the new European standard on daylight in buildings. So this was a game changer because for the first time there was a hint towards simulation in there, and it took such a long time just to have simulation named in a standard like this. But then the standard is still made up of endless tables and endless numbers just on a PDF copy, and also all sorts of different calculations that just hint toward the use of pen and paper to calculate things, to check compliance with this norm. And it really makes little sense for me that we go so far ahead with simulation methods and analysis, and then we have to comply with norms that are so out of their time. I don't know. So what I would also like to see is that something, if regulation could behave more like scripting, like computer coding, and then being more interactive and being easier to check, like have a standardized code. It would be so much easier to check compliance, so much better, more interesting to progress with this. And last, as for collaboration, I would promote among all the students the existence and the participation with different professional associations that are there, and that they also need to evolve together with all the rest, all the building simulation analysis. And so they need to take up new blood and to maybe also change the way we collaborate with each other. But the important thing is that we create situations like this one or others where we can discuss ideas and start collaboration. And I think IBIPSA, for example, is doing a great job in organizing conferences and meetings or webinars, or also it has its own scientific journal, and there is space for everyone to participate actively or less actively. And for example, there is also a student competition which should open soon, and which all of you could potentially participate. And so I encourage you to check these up. And just thanks a lot for listening.
Thank you, Eleonora. That was fascinating, and I certainly learned quite a lot during that. So now we have approximately 10 minutes during which we can take questions specifically for Eleonora. If you've got a question, could you please raise your hand in using Zoom, and we will, there's Cheng and I will be both keeping an eye on things as we go through this. I'll start with a question though, Eleonora. How do you see, so obviously you're talking potentially at quite very high resolution but a relatively small sort of within individual buildings or and spaces. How do you see daylighting and our understanding of how we simulate that moving together with the tendency towards sort of larger urban scale simulations and some of the challenges there, which is also increasing complexity, but a different element of the modelling that's becoming more complex?
So right now one of the challenges with daylighting used to be the time that it needs to to compute and to get the results is slightly, yeah, if you want an accurate, some accurate result, you need to wait generally more than thermal analysis, let's say. So at urban level, that can be a bit annoying. But it got really much better, and now there are new simulation software that can handle larger masses. And also, if you just look at the outside, then it's generally okay. If you then want to look at urban level, but also the indoor elements, then it gets complicated. So anyway, apart from the technicalities, as for when I think about urban and daylight, what I care the most is to make sure that we think of daylight as not like as something that we really need, not just a commodity. And the way that cities are growing and becoming denser, it's sometimes a bit worrying from the daylight perspective. It really needs to be assessed upfront, and we really need to remember that if you live at a ground floor in a highly dense environment and you barely go out, then it's not good for your health. and yeah, so it's good. Yeah, I would just.
Thank you. That's really interesting. I suppose the other part of that I wonder about from the work that I do, which is more kind of on the urban scale, is also about data and actually having, how we collect the data to accurately characterize people within that urban environment and people's experience of that urban environment within simulation. I know Farhang's going to talk to us about occupancy later on, but even in the task that we set the students for last week's session, where they were monitoring their own living rooms, in most cases, if you had two people in one apartment, that was relatively straightforward. But as soon as you had more, I said, as in my case, 4 of us living in this house, even just knowing whether the blinds are open or the lights are on all the time, it becomes quite challenging, and that's in one room, in one family house. So it's quite a challenge, I think.
Yeah, and also, I don't know exactly how you do it, but also material characterization for daylight assessment, for example. If you take a urban context, it becomes really challenging then to understand what you like, the reflectance, for example, from different glazed buildings or other opaque surfaces. So it can potentially really give you a different result.
Yeah, that's very interesting, because one of the challenges at urban scale is obviously having an urban model that captures the interactions between buildings, rather than having an urban model which is a collection of buildings which are effectively standalone. But obviously the complexity of that is increasing exponentially.
Then one of the emerging topic actually is this study of interreflection between highly glazed buildings, because they give you, they can really, blind you, or in worst case, as we all know, the walkie-talkie and concave surfaces, and it can lead to worse damage. So it's
in that case, that's if people don't know, that's a building in the City of London, which I think resulted in some cars melting, didn't it?
Some very expensive car that made the first line in the news.
Yeah, absolutely. Okay, well, that was great, Eleanor. Thank you so much. I really enjoyed that, and I'm sure everybody else did too. And I hope that if you have questions for others later on, you'll jump in, and also that people who have perhaps been prompted to think of questions for you will join in the panel discussion. We'll move on now to Dru. Dru Crawley from Bentley Systems. I'm going to let you introduce yourself because Eleonora did such a brilliant job of that. Do you, will you be sharing your own presentation? Or would you like...
Let's try and see if I can.
Okay, perfect.
Does that work? Okay, good. Well, good afternoon, everyone. Morning here for me. I'm Dru Crawley, a Bentley Fellow and Director of Building Performance Research at Bentley. And I'm going to give you kind of not a lot of words on slides, but more images, because I think one of the exciting things that's happening in simulation is the ability to capture information that before was difficult or costly or other things. And and right toward the end, I've got something interesting to share. Just as a bit of background, my undergraduate degree is architecture. Actually got licensed to practice, never really did. I've always been in the building area. I also have a PhD from Strathclyde as well. So let's, so I'm going to continue on the topic of digital twin, and I got to find my mouse. Okay. And the idea there is to capture or have an image of what you're trying to capture. Most of the digital twins that we talk about today are really at the infrastructure level, the city scale, or even into community, etc. The interesting thing about it, it's not a single means of capture. You don't have to, as we saw in this picture of Paris, this twin of Paris, we don't have to have everything come from the air. We can capture things from the ground as well. It's no longer just a single device being able to do this. The expensive scanners of the past, of the LiDAR, etc., now can be replaced even by, as you can see in the bottom, your cell phone, and that's kind of a real big change there as well. So the ability to pull that together has been kind of one of the key things that's happening, and that federation of data is a key thing. So, but now with the cell phones, we can go in and capture what is in reality, and then be able to, because the images are so accurate, being able to measure them. This case, just uploading photos, and then in a few minutes being able to bring back what is an accurate 3D representation of whatever the object is. This is a kind of a case study we did. This is Philadelphia, and the Pope was visiting, so they captured, for security purposes, they wanted to look at security on the Pope's route. But what we did was take the benchmarking data that's a public database about energy use and water use in various buildings. Any building over about 5,000 square meters does have data published for that. So we were able to overlay the two of them within the same model. And I think that's kind of the idea of the federation. So it can be the nice fly through that you see there, but also behind that is all the information about each of the spaces or the buildings. We can sort that on energy use. We can look at any of the different other metadata that's available about that. So we can begin to identify very quickly what's going on in various areas. And I know work there at UCL on this has been progressing quite a bit. US less so. We do have these databases, but they're not being integrated at the visual level. Also, this is, let's see, why is this not going? And I'm sorry, it's not supposed to play music. This is, instead of using photographs, it's taking thermography kind of to the next level and using the thermographs in to create that same visual model. And this is a professor at Georgia Tech in Atlanta is working on this right now, trying to capture quickly through thermography and drones, being able to look at opportunities for retrofit on a large scale. So you can take a drone, fly a neighborhood, and identify the top 10 projects that you need to work on. So that ability to capture information is good. One of the other things that I've seen that's been interesting, and this is using occupant modeling and looking at how, in this case, we're looking at safety and security, but and traffic, and being able just to see real-time changes within the within that and how we can affect it. At the same time, the same agent-based modeling can be used to, we can more correctly simulate what's going on in the space and how people interact. And because most of the, well, all the thermal simulations I've ever done, people have been a percentage of their time in the space. It's not actually how they interact within the space or how they can move forward. Moving on to city scale again, this is Helsinki. This is the third generation mesh that they've created. They were able to use some machine learning techniques, deep learning, to automatically begin identifying sub-elements of that. And that work is continuing today. I'll show you. This is some images from the iNumber project, which is both there at UCL and at CEPT University in Ahmedabad. And they're creating a 250 square kilometer model of the entire city. Their intent is to take that, use the deep learning, machine learning, and automatically create some of the building elements, identify the parts of the building, and then merge that with the databases that exist about the buildings. The other interesting thing that I've just been seeing recently, the new iPhone Pro has LiDAR built in. This is an image I just captured off the web that you can wander through the space and begin to capture that sort of detail without a lot of effort. You're just taking the camera and going around, and you can see in real time what's going on there. So that sort of piece of it has not been possible before. A lot of the systems that are don't do well with glass. Glass, because of the reflection and the transparency, doesn't provide a surface for the photogrammetry to really deal with. But this may be a way for us to capture models very quickly, because they are quite accurate, just because of the process that's used. And I've watched several webinars about this in the last 2 weeks, and they are it is remarkable what you can capture in basically real time as you're walking through. So one of the things that the digital twin and the idea of this is that we can be simulation at a different scale, where we're being able to not only capture interiors and exteriors of existing spaces, we can merge those with the BIM models, and then they can interact with the rest of the infrastructure, our renewables, our energy, water systems, road, storm, and rail. So I will leave it with that and be happy to answer any questions.
Thank you, Dru. That was excellent. Very exciting work that's happening there at a completely different scale. Does anybody have any questions for Dru?
Yeah, I have a question.
Yes, please.
Yeah, so a general one is that, so we have now building modeling. We have now some visualized control system in some commercial buildings. So what's the relationship between the digital twins and these existing applications? Are they some sort of integration of this?
Yes, that's actually, I have another video I should have shown. We did a test case. Microsoft has a new Southeast Asia headquarters in Singapore, and starting with the BIM model of the space, they were able then to locate the control points, both the measurements and and to be able to start looking at collecting data actually within the digital twin on how the building's being operated, where occupants are, etc. So that the digital twin forms kind of the basis, the 3D platform, as you will, for collecting or being able to associate data. And that is one of the things that is moving forward now.
Okay, thanks.
Thank you. Tim, would you like to ask your question?
Yeah. Hi, Dru. Tim Dwyer.
Hi, Tim.
Thanks for that. Really interesting presentation. I'm afraid my bandwidth from my home isn't that good, so you won't be able to see me. You can hear me, hopefully.
Yes.
I've seen quite a few of those images of someone holding a camera up, and then the next screenshot shows a wonderful 3D image. I just wonder how much processing there is and how realistic it is for us to expect to be able to go and do that in buildings with, even if we are able to afford an iPhone 12 Pro in the near future. Is this something we can really realistically?
Oh, it's realistic. I couldn't find a video quickly to be able to show it, but I've seen images where people are wandering through the space, and there are different software for use on the phone, but it is a real time as you're wandering through the space. It's populating the mesh as you move it around, and if you have gaps, you just go back and re-image it, and it's remarkably quick. I won't say it's inexpensive. The iPhone 12 is not a cheap phone. It's, I think, on the order of $1,100 or $1,200 here, but it is cheaper than any other source I've seen. You saw the image where one of my colleagues was taking pictures of the piping configuration with his phone. He's taking separate images there. The iPhone Pro, you literally are walking through capturing, and you can see that on your phone as you're doing that.
Thank you. That's really exciting stuff. I wonder could you tell us a wee bit more about how the machine learning side of things is developing, and what the kind of focus and the challenges are there?
That's one of the things that's kind of a new piece for us, that we already have a lot of information within these digital models, the twins, for example, and it takes a bit of training of the system to be able to help it understand within a set of images what it's looking for, to be able to identify what's a roof, what are walls, what are windows, etc. And it, as you saw in the image of Helsinki, they did it pretty quickly just to show that they could do roofs and trees and what are roadways. So I think that's it. I mean, the techniques are not new, the deep learning techniques that are there, but it's mostly training the model the first time through to be able to have it understand what it is it's looking for, and that's really the challenges there. And let's see if I can. If you look here, this is SEP's attempt to take a look at it both at the digital twin side, but also looking using machine learning to detect that, and they're finding good success for that. And I think partly because of the elements are similar in color and scale, and they tend to be flat in Omnibot, which is less of a challenge. But so it is kind of a new area. We've been working in machine learning for 5 or 6 years, but recently making this available through products is new.
Thank you, Dru. Are there any other questions for Dru, or shall we move on to Marc? Okay, that's great. There'll obviously be another chance to ask questions at the end of this, of everybody. Thank you so much, Dru. That was really interesting. So now, Marc, would you unmute yourself and share your screen, please?
Okay, do you hear me?
I do, yes, thank you.
That's already solved. Okay, I guess you see my first slide?
Not yet.
Not yet? Oh, just a second. Screen.
Yes, now we do, thank you.
So I have actually a quite similar background like Dru. I'm an engineer architect, and after only actually a few months in practice, I went back to research, and actually motivated usually by where the research really fits and matches applications in real life. You received a paper I heard from Pamela about the 10 challenges for simulations, and the first one there was trying to shift slides. Bridging the performance gap. That was actually the main core also of my PhD, but I won't go much into detail. I will just take it as a lead to actually introduce a few of the topics I want to like highlight, some things I think are like really changing or motivating within simulations, building simulations. Now, the performance gap, I think, is a very known issue. This is a chart from a study in the Netherlands on 200,000 houses. I would have liked to show data from Belgium. We have it, but I'm not authorized yet to show it, so I hope within a few months. But the results are absolutely about the same. So what you see here is an evolution of theoretical energy performance levels in the darker red bars from low to high performance levels, compared to actually the real, with a big saving expected across performance levels, but a much, much lower evolution if you look at real energy use, with savings which are like 1/3 of the expected savings. And many people would say, okay, but we should go to more complex simulations, more advanced simulations, and it's because we simplify things. And I want to actually like to pierce that bubble a bit to start from. By giving one example of a study around Robin tests from Annex 58 of the International Energy Agency. I've heard you also had a simulation exercise with a shoebox trying to compare results. And this was about the same. It was a project for which one building in Holzkirchen at Fraunhofer Institute was measured with many, many sensors across all rooms. And the data was given to the different research group with the question, try to simulate this building and let's compare results. And the experiment of that building was actually like this. It had different phases. A first phase with a constant temperature and people had to predict the heat input. Second phase was with a varying heat input and the research team had to predict the temperature. Then again, fixed temperature predicts the heat input, and it ended with a period where that building, everything was switched off and it was free floating and asking people to try to predict the temperature in that building. And they could use, it was oral research group across the world, and they were allowed to use actually the simulation tool they preferred. And researchers tend to have some pride, so they try to put a lot of time in it and to really do their best. But comparing result was quite dramatic. If you see from the free floating, I'm just doing one chart. These are results from 9 of the groups participating, comparing the temperatures they calculated with their best models, after actually already a second step where they got the good results, the accurate measurements, and were able to try to find their errors. And still the different groups had like differences of up to 5 degrees Celsius in predicted temperature in the living room of that house. And this is related to many types of uncertainty you have in a house. So don't think that that's going very far in your simulation will solve everything. And in real life, you don't even have those inputs. You might wonder what people or how people heat a building, but just to give an idea of that uncertainty, I won't go into detail into user behavior because I think the next speaker will. But this is, for example, findings where we compared what people told us was their set point temperature on the y-axis, compared to what we deduced as a set point temperature based on the measurement. And there was even no link, no correlation between what people told was a set point temperature and the real one. So I would say with all the challenges and all the advances in simulations, keep also your goals realistic. And I think the challenges and the potential lies somewhere else. It's coupling with other sciences, because in the end, we are just applied scientists and the big potential is really to find their links. I will go into examples later. I think very often actually reducing complexity rather than going very far into complexity, because you tend to forget the most important things like uncertainty of inputs. And for those uncertainty of inputs, using the availability of big and real data, something really evolving in the last years. And in the end, integrating this within actually a logic, like a business logic. Coupling with other science, I guess the next speaker will probably say more about user behavior, but my main message is actually every possible research field we are connected to, you can actually start a multidisciplinary project, couple the methods from the two, and make something new which is relevant. And this happened, for example, with a colleague who worked on Legionella in buildings, where you know that Legionella is a bacteria within water, which actually grows around 30 to 40 degrees Celsius. That's why we usually try to heat our storage tanks to maybe 60 degrees. And instead of just using those rules, she coupled thermal modeling and bacteriological modeling to be able to have a very better way of simulating and predicting bacteria grow and to save energy. And the results were that good that actually a spin-off is starting now, which I'm co-promoter of, where we try to integrate that in control algorithms, where we move from the simulation models in a computer towards integrating simulation models into the boiler tank or coupled between online computing and boiler. That means that the challenge is not about having the most accurate model. The challenge will be about simplifying your model, making it integrated in a very, very simple processor in a boiler, not in a big computer, and having it very robust, not having like a researcher behind his computer who can solve every bug which is happening, but something which actually, you know, if you launch it, it's going to work. And if it doesn't work, at least it won't explode. I'm like exaggerating. The challenges and the goals are different. And it also shows that the integration means that not only an integration of different fields, but also an integration within a valorization logic, which might be a business logic. Simulations in research is something else than simulation with companies. One of the projects we just finished with a company was actually looking at integrating simulation in the whole process of the company, from the market targeting, trying to find which are potential clients through a stock analysis, onto using simulation models in their R&D, trying to improve their ventilation systems and HVAC system, but also using those same simulation models in sales, where actually you're not trying to estimate a whole stock that you might target, but you have a specific client and you want quickly the salesperson that has no expertise in simulation to use pre-made simulations to give advice. So the challenge there was totally different. The challenge there was trying to understand the whole stock, which is a potential target market of a company, by analyzing different climate and different typologies. And based on that, making models, complex enough models to really actually analyze everything they want to analyze in their company and optimize, like control strategies, etc. But also with a challenge of integrating that in a whole business logic, meaning that we would say, okay, as a researcher, we use this as a simulation tool, which is the best simulation tool. But in a company, they already had another tool. We use Daimler for building physics simulation, but they use, for example, MATLAB for programming their control algorithms, allowing them to compile them directly to controllers. They don't want to have two separate things. They want to integrate that. So we had to find a way to actually couple their control algorithms in MATLAB with our building physics model in Daimler for them to be able to use one and the same line of code for the control algorithms, both for building simulation, but also once in the R&D they see, okay, it works, to really compile that directly to the controller of their ventilation system. So integrating was much more than just a challenge of integrating simulation software. It's a challenge of integrating that in the whole logic of the company. And one big thing that also evolves there is that not only we as a researcher, but also actually the companies tend to be more and more sitting on big real data. Big real data that we can valorize as a researcher, but that they can also valorize as a company in R&D or something else. For example, the direct competitor of that company I just mentioned, we also work together. We are very open about them. They know it about each other. But they have, for example, their ventilation system cloud connected, more than a few thousands of them already, which gives us a tremendous amount of data on temperature, humidity, CO2 levels, etc., and all the different rooms of a house. And of course, they do that to have a very nice image on a smartphone, try to like link the customers to them. But of course, for them, it's very interesting data for R&D, for example. And that is something that you see in general. We also always see smart buildings, and we think about smart buildings as being like a possibility to improve things. But actually, I think simulation might help buildings become smarter, but actually smart appliances will also improve simulations. And why? It's because we are collecting data and we are really testing things. For example, we have now a new Annex 86 of the Energy Agency on actually energy efficient ventilation system, and subtask 5 that I'm co-leading is actually focusing on the use of that big data within those systems for many different reasons. It can be offline use, trying to understand how things work, improve scientific knowledge, targeting the market, etc. It can be online use, in real time, using that data coming in, coupling that with models to do, for example, predictive controls, to give feedback to the users, to do continuous optimization. And often in all those steps, models in some or other way are taking a crucial role. But of course, it opens totally new business cases also. I won't go into detail, but that's very interesting about it, is that it opens totally new business cases to research. And that data, of course, is data that we do analyze also at stock level. If we try to renovate our building stock, we have the big challenge of getting all that data together and trying to solve the performance gap. And we know we have big data, but one of the big challenges with that data is actually linking that data. And I think that's very important to realize. If you look at, for example, the data sources in Belgium about buildings, there are numerous. We can go like, I think, 5 or 10 different governmental agencies having their own databases, which are not coupled. Companies have their databases. One database is on address level. The other database is, for example, on people ID level. The other database is actually on gas meter level, which might not match an address. And it's a big challenge to try to map that all and to bring that together. So this was, for example, an exercise done by master thesis students trying to map all potential data sets which might be relevant for us in Belgium. But a next challenge, I think, for that data is actually unlinking that data. You get data which is a result actually of what is existing. For example, if you want to use that data for policy advice and you analyze data on building stock from the governmental database, know that that data is a result from the policy. For example, here you see a distribution of the K level is an insulation performance level in Belgium across different typologies. And you see here, for example, the houses with a high performance, the passive houses, which got specific subsidies, or you get here a very straight line because at a certain moment you had to reach that level for performance regulation. So the data you are analyzing is biased, is a result itself from the policy that you try to give advice to. So it's very difficult to unlink those things. And the same happens with, for example, data on user. We saw this is, I won't go into detail, but heating patterns in old houses and new houses across 24 hours of the day. And what is mainly important to see is you see the green line was a probability of heating a living room, and the yellow line, the probability of heating the bathroom. And switching to a new neighborhood, suddenly people started to heat differently. But trying to understand what is actually the cause of the building, what is the cause of the user is very challenging, but is crucial if you want to use that data. And then, of course, you can try to implement that in models, simplified models usually, because I'm quite a big, I'm always in favor of simplified models if you can simplify things. So, for example, you can go from EPB, it's like the standard assessment procedure in Great Britain, the SAP in Great Britain. Single zone, you can try to make it multi-zone to take into account users, but always realize in practice you have to be able to feed that data. You have to be able to have that data. Nobody wants to measure every single door and step in a house. So we were facing the challenge of, okay, how will we scale that up? Again, working with other colleagues, multidisciplinary, worked with the people in BIM, coupled the building physics model with their models. And actually then we tried to find a solution to generate those models automatically. We had, for example, data from an professional assessment method, but very simplified. We know nothing about the interior of that building. So what we did is we made actually all typologies of houses, multi-zone in detail. And depending on your house, we select a typology which is more similar to yours. And then we fit that typology to your house. So for example, we know you have a detached house. We know everything about the exterior envelope. We know nothing about the interior. We take a typology very similar, and then we skew and fit it to yours. And suddenly we have actually made a fake model of your house that we can use. It's like some kind of rudimentary white box approach of increasing knowledge. But the great thing now is that you don't only have that data, you can automize it to building stock levels and automize all those things. But now we have also the real energy use data. And now we see a shift towards actually data-driven modeling, where we totally skip all those physical modeling, all those assumptions that we make, and we really create data-driven models that directly take building properties and real energy properties, and we try to make direct predictions of energy uses. We can have lots of discussions about that. I love those models, but I do have a lot of comments about them. And I think the future is actually in between. I think the future is in the gray zone, where you use the real energy use data to actually tweak it, to add a data-driven layer above the white box layer in such a way that you still understand your models, but that you can make much more accurate models. And I think that would be a totally separate topic of presentation, but I will finish here. Thank you.
Thank you, Marc. That was very illuminating. I think, does anybody have any questions just now for Marc? Either put something in the chat or raise your hand. I'm going to see, I can't see any hands raised at the moment. I was just wondering, Marc, then, could you tell us a little bit more about this evolution that you see in terms of how you, I think the key bit that struck me was how you overlay the real data but still have a model you understand, because obviously the challenge is that the real data explains the current situation, and you can build data-driven models that tell you what's happening now. And the reason that we use simulation is typically because we want to be able not just to understand what we're doing now, but we want to do something which changes the underlying physical processes. So the building physics changes, which means that the real data may not actually, that model developed from the real data may not tell us very much, because the processes that are hidden in that black box are now different. So your comment about still having a model you understand is really important, I think.
I think that's a big difference between a white box model, which is really first principle based, where you really know all your components, and from physics you build it bottom up, and a data-driven model for which you don't need to know anything in theory, and you just have like machine learning trying to replace your. But indeed, the issue is with data-driven, it only applies to the scope and the range of the sample you have trained it to. And indeed, then your model will fail from the moment you have, for example, technological innovation. You can't grasp it. However, if you stick to the white box, it's very hard to solve all the problems, because I think it's like an utopia to think we can make the best possible white box model which will be accurate. I've seen too many trials, and I don't think we will ever succeed. It doesn't mean it's not relevant. So I think the issue is combining. We see a lot of evolutions where, for example, even in neural networks, combining neural networks with, for example, physical modeling. And ideally, I would like to have the black part reduced as much as possible, the white part as big as possible, to find a pragmatic balance. And the idea there, of course, is to be able to have a more probability that the extrapolation would work. The interpolation within your system training sets, which in theory anyways should be good, but extrapolation not. There is no clear solution, but I think actually even in a white box model, I've actually yet to see actually a real white box model. Because if you think about it, even for example, in SAPs, SAP, quasi-steady state methods, utilization factors are actually just a regression through thousands of simulations, which you could actually call actually something black. Even the fact that, for example, use transfer functions in some models like Transys actually is not totally white anymore, because there's actually all things that have been trained on previous simulations. So I don't even believe that white box model exists, and I don't believe that black box model exists, because you always set some limits. So actually, that's my big comment, and it's always finding a balance.
no, I think that's really interesting. It's quite perhaps a controversial point that white box models don't exist, but there clearly is a good degree of truth in that. I think one of the other things that I think will have been particularly interesting for the students on our MSc module will have been looking at the round robin tests from Annex 54, because we asked them to do some modelling of their own and to effectively to replicate 2 of the best test cases. So they understand some of the challenges, I think, in terms of, for most of them as beginning in their career as building simulation experts, of just replicating, even with the very, very simple shoebox model, to be able to understand how many different inputs there were potentially, and to gather all of the data for those and the assumptions that one might make. And I wonder if you could just tell us a little bit more about the conclusions of that exercise, because it's quite striking to see these groups of really expert people who are still finding very different results.
Yeah. Well, to be clear, this is not a project I led. We participated as one of the groups. It was actually led by both Farhang, who has much more expertise on that. And the full report is public for who wants to look at it. But I think the main thing is that actually most of the models were able to predict the same phenomena. And that's very important. Most of the models were able to have like the same trends. Like you see actually here, you have offsets and it diverges. However, for example, checking the reaction of the building to, for example, the fact that suddenly there is a cloud before and in front of the sun, or something else, those models were able to see that. The absolute values, however, were often not accurate. And that, for me, is the main reason why you should also always think what you use that model for. Do you want to make an absolute prediction, or do you want to try to understand how it would react and tweak and improve that? I'm more in favor of the latter than of the former. But important to know, of course, is that all those models were quite different. For example, like I said, if you use trances, you have transfer function, not finite element functions. And each model, like ESPR, you can choose if your radiation is really a gray radiation, or if you use star nodes functions. So in each model and each simulation software, you have many options about simplifying things. And it all has impact, and you really have to understand what is in the background of those models. And that is, for me, also my biggest fear for the moment in building simulation. It's getting that easy to use. And because of that, it's getting more and more used also in practice by companies. But you end up with something that people less and less know what is in the background of it. And it starts to become actually a black box. And what we all tend to give as a comment, for example, to SAP or other EPB methods, which are simplified, is actually happening now also with that. And you have to show it, and you have to understand it. And that's also a reason why I'm in favor of simplifying sometimes models, because sometimes I prefer to have a simple model which may be a little bit less accurate, but if it allows you to do a sensitivity analysis, and instead of running it once, running it, for example, 100 times and knowing an uncertainty on your model, I might be in favor of having 100 uncertain model with a feeling of uncertainty, rather than one very detailed model with no idea actually of how good it fits. And that would be like the big message.
Thank you. I think that's a great point to end on. I hope all of our students read the paper that they were assigned last week, which was about fit for purpose modelling, which dealt with this precisely around the challenges of increasing approximations and when your model becomes increasingly complex, you have increasing uncertainty because you have so many different inputs that you may just not have good values for. Whereas when you have a simpler model, you have other sources of error, and there can be this sweet spot in those two curves, which is something that we touched on, I think, in the very first session that we had, but the paper last week was specifically in relation to occupant modelling. So it gives us a nice link into talking to our next speaker, Farhang, on occupant modelling. So Farhang, if you could just unmute yourself and I will spotlight you.
Hello, thank you. Yes.
There we go. Thank you.
To share my screen. Hello, everybody. Very exciting presentations. I really enjoyed it. And this one is about occupant behavior modeling. And it's interesting that at different points in the presentations, we talked about occupant behavior, and now we can see it from another view. So a bit about myself, as you asked, I updated this slide. So I am a lecturer now at UCL IDE, and I did my PhD in Vienna, TU Wien, and my master's in low energy architecture. And the key area of research for me has been building performance simulation and occupant behavior. I start by asking why occupant behavior matters for us if we do building performance simulation. And a key argument that has been used quite frequently is that occupants have large impact on building performance, both in terms of the passive impact with their present, with their internal heat gains, and also with their active impact in terms of interacting with the building systems. And always we refer to this kind of situation that you see on the right-hand side, that if you look into identical buildings with thermal characteristics similar, but you may observe very different energy use values. And we commonly refer to that to the different occupancy and occupant behavior. Also, we argue that with the emerging high-performance buildings, the proportions of energy use in the buildings are changing. So if, for example, this is from Canada, if, for example, 30 years ago, the space heating was the dominant component, today it might be different. It might be the use of different equipment that occupants have much more control about, as they are not that much weather dominated. And also the other issue that makes us interested in occupant behavior is the notion of performance gap that you heard about before. And by that we refer to the differences between what you predict, what you simulate, and what happens in reality. And due to this difference that you saw that in these energy patterns in different buildings, so it is very hard to do predictions, of course, we see that. So we believe that if we have better models of occupants, we can do better estimations. So with that, I come to introduce to you and have a recap of what the most common approach to model occupant is. I assume you have tried this. And you know that we typically represent occupants in building energy simulation with schedules for presence, lights, and electric equipment for different types of building and different types of the days. But recently in IEA Annex 79, we did a review of international building energy codes in 22 countries. We looked how they represent occupants. We realized that almost all of them neglect the occupants' interactions with the building systems, such as windows, shade, thermostats, and so on. And they still stick to those sets of schedules and design values for equipment, light, and presence. So what I would argue is that a key thing is missing here, and that's the fact that we assume that occupants are passive recipients of the building indoor environment. But in reality, if you look down here, it's actually it is actually like that the occupants are exposed in an indoor environment, in our built environments, and they do some adaptive actions depending on the type of the building to change the conditions of the building. So that interaction is commonly overlooked in our building simulations. So As a result, it is quite a few years now that we talk about new generations of occupant behavior models that one can say can have 4 characteristics, as I have listed here. First of all, they are dynamic, meaning that they interact with the building systems. For example, they capture if and at which conditions occupants open the windows or not. And they are commonly stochastic, but not necessarily, meaning that they work based on probabilities, and they are explicitly data-driven, not in the sense of black box, but in the sense of that we look into some data, some observation, and we try to get a model out of it that explains the occupant behavior. And also they can be agent-based, meaning that we don't treat occupants as a whole group in the building, but we treat different types or different persons in the building. So just to make it maybe more tangible for you, I report quickly on a study that we did in Vienna. That was an office building, and we focused on the window operation. And we tested some of the existing models, and we developed our own models to come to some understanding to which extent these occupant behavior models help us to have more reliable estimations of building energy use, but also to find recommendations for use of models in future. So we first started by looking in a hypothetical situation, what is the impact of window opening in this office? So we said, what happens if I keep all the windows open all the time? So I come to this hypothetical very high annual heating demand. And if I close the windows all the time, that would be the heating demand that I have. So that's the range of uncertainty, hypothetically. Okay, so that's the impact that we have. But where are, how the occupants have actually operated the window and what is the resulting heating demand? So we saw that it's just slightly above the minimum. Why? Because occupants do not tend to open windows, especially in Vienna, that much during the heating season. So that's the reality. That's our ground truths. Then we tested some of the existing models. Those stochastic ones that we are proud of, that are published in very recent research. We try to use them without doing any changes, just based on the research previously done. And we realized that the results can be quite off, and without any calibration, without any adjustment. So there was no easy solution, we understood. Just an advanced, sophisticated model does not necessarily help us much. So we started to adjusting them. For example, we took care of the night ventilation patterns, and also we started to calibrate them based on our own data. We started to retrain the models, and we realized that the results are getting better and better. But maybe perhaps to some extent, surprisingly, we realized that if we set some very simple non-stochastic models in terms of some rules of occupants' interaction with windows, depending on temperature, we are also not that much off. So coming from this point, we try to develop our own models and see what model would be best fitting for what we want to do. I just draw your attention that we were in Vienna, and even in 2011, quite some years ago, we had temperatures above 35 degrees. So the summers could be quite hot, and we tried to capture this situation. We started by a window operation model. To just give you an example, that takes indoor and outdoor temperature to give you the probability of opening the window. Okay, so you see outdoor temperature here, indoor temperature here, and the model response is the probability that the window will be open. For example, this first model tells us if the outdoor temperature is 10 degrees and the indoor is 22 degrees, the probability of opening is quite low. The model is working well quite here, but we realized that in very hot temperatures outdoor, it doesn't do a very good job, because that was not what's happening. If the outdoor was 35 or above, people are not opening the windows that often. So we realized that the models developed somewhere else, for example, in the UK, didn't work that well in the Vienna for us. So we started to tailor the model for ourselves, and we considered interaction term between indoor and outdoor to this simple model. And as a result, we have this situation that now if the temperature is very high outdoor, then the people do not open the window very much. Whereas if you have like 32 degree, 30 degree inside, and the outdoor is pleasantly 20 degree, then it is very likely that the people open the window. And we did this for different people. So a resolution of individual people or aggregate for all occupants. And then we tested it to see when we need to use which model. So we focused on 3 performance indicators: annual heating demand, peak heating demand, and time outside comfort zone. in free running season, and to see where we want to use which model. So we had the aggregate model based on this modeling that we did, individual models, and a simple model, just a rule. If the temperature is about 26, the windows are open. And we realized that actually for annual heating demand, the error is low, and we can do as well quite good with the simple model. But when it came to peak heating demand, we realized that this rule-based model can give us quite a large underestimation of peak demand, because it doesn't capture the fact that anyway people might open the window a bit sometimes in the windows. And also the simple models did not do very well in terms of comfort assessment in summer. So that is just to give an idea that really, if you want to go for fit for purpose model, it does not only depend on the location, on the building type, but it also depends on the type of a study, on the type of performance indicator that we are interested in. So I just conclude my presentation by saying that this is a very young field of research, and we are also in Annex 79 in the International Energy Agency, Annex 79, and we want to push this further to come up with fit for purpose occupant behavior models for occupant-centric simulation-aided design. And for example, we are now working on a book. We hope it will be published in 3 years. So it's very early stages, but we are a team of researchers that we think this is an important topic that it need to be further addressed. Thank you.
Thank you, Farhang. That was another excellent and very informative presentation. Does anybody have any questions for Farhang just now? Okay, so so Farhang, I think I have a question about how the data is collected. What level of diversity we have of occupants in the in some of these models in the first place. So one of the things that I'm interested in my research, we're looking at slums in 2 cities, in Ahmedabad and in Lima, and this is a project that Dru's involved in through Bentley Systems. They're supporting us, and Ivan is as well. And one of the things that we're concerned about is, as we move these models created in cities like Vienna or London or wherever, and we start to try to apply them in cities in the global south, we may have very different sets of behaviors, and people who behave, people whose whole lifestyles are just not captured in the assumptions that underlie all of this, and how can we address that? And I just wondered if you have to comment on that.
Yeah, absolutely. That's a very critical issue, and we need some observations, some empirical data to be able to estimate a more or less reliable representation of occupants. In this case, for example, so it was a test case, so we had a very high resolution of data. We had motion detectors for each occupant, and each occupant had access to one window, and that window was monitored with the contact sensor. So that helped us to have like individual models and aggregate models and compare the necessity for using that. But of course, I can imagine location that you talked about. Definitely situation can be quite different. For example, just for comparison, to highlight it again, the difference between models in Switzerland and UK with the situation that we had in Vienna was quite dramatic. They did not consider the situation that the outdoor is so hot, even in Vienna, that there are times in summer that people do not like to open the windows anymore. They don't think it helps, and quite rightly. So I can imagine in India that can be quite more dramatic, and we need local data to do that.
So how do you, for example, in residential, if you were looking at a residential study, how do you go about collecting that data?
Actually, very recently we had a study in a number of flats in East London, and we were lucky that they gave us permission to have again the same situation: contact sensors for windows and motion detectors for presence. Even though it is very hard to get at least motion detectors in residential buildings, but we could do that. So I think it is possible in residential if you totally convince the residents that their privacy is respected, and that will be something that has also some benefits for us. For example, the study that we did involved also testing a air filtration unit. So one benefit for the residents was that they had the chance to use this equipment for a while, and also at some points it was involved also vouchers and things like that next to it, so that they are happy to live with some annoying sensors for a while.
Yeah. How long was a while in that case?
We had close to 1 year, I think.
Okay.
Yeah.
And are you able to leave the sensors in place for that period, or are you going in repeatedly to download data?
Yeah, that depends, of course, on your data logging procedures. If you have connected things, that would make everything easier, so that you can just remotely check that the sensors are working, because many things happen. You can never rely on sensors. We had a combination, for example, some of the contact sensors was just logging the data locally, but the best solution is, of course, if you can set up, I'm not that expert in such things, but if you can set up some internet connection and check the data remotely, and just need to go there for very problematic situations, that of course would be the best possibility.
Yes, one of the challenges that we have is that, well, like most places, but Lima and Ahmedabad are both have quite severe outbreaks of COVID-19 at the moment, which has suddenly made the whole research design well, a new question that needs to be asked again, because of the challenges there. So obviously not the biggest issue that people face, but certainly one for the project team to think hard about. So thank you, Farhang. That was great.
My pleasure. Thank you.
Thank you. I'm going to ask you to stop sharing your screen now, and ask all the speakers if they would mind just turning their cameras back on. We now have an opportunity. We have about, I'd say probably about half an hour, because we probably need a couple of minutes for closing remarks. I will, apologies Farhang, I will just unspotlight you so that you don't have to be full screen for everybody. Oh no, it's me now on my screen, so that's unfortunate. Let's I'm going to have a gallery view. So one of the things that I thought would be particularly interesting here is when we have a panel of such experts with diverse expertise as well. So there's a core here of simulation, of working on buildings, and then very different directions that people are taking it in, whether that's daylighting in Eleonora's case, looking at the occupancy as Farhang does, the kind of applications and products at the urban scale, and using the remote sensing in the way that Dru has been doing recently, or Marc bringing in some of the sensor data. Now it's all very interlinked, and what I wanted to do was to give everybody a chance to ask questions that were not just specific to one presentation, but to get a perspective from all of the panel on that. So for this, I would very much appreciate it if you would turn your camera on if you are one of the participants and you want to ask a question, please, because it's nice for the speakers to be able to see who's asking a question. So who has a question first, please? Ivan, on you go.
Yeah, hello. So I can't find how to raise the hand in the Zoom, so
no.
that option might not be available.
Okay.
But general question, I think Marc mentioned in one of his slides co-simulation and the FMI, FMU, stuff like that. So my question for the panel is your opinion on the impact of co-simulation as a approach in modeling technique in a future next generation tool of simulation tools in general? So is that going to be good, going up, high, much significant and much higher use of co-simulation, or is going to be limited to very specific cases, as we saw, for example, control strategies and stuff like that?
Who would like to go first?
I might say a few things. Well, first of all, like many of the topics actually addressed today, it's not new at all. So I think we often tend to think that what we are working on is very, how to say, like a hype of the moment and the next big thing. But if we talk about BIM co-simulation, even user behavior in the 70s and the 80s, it will all already in some way studied. So the question is, will it rise? I think many people have said in the past, yes, and it still hasn't, about all these different topics. So I won't make a prediction. About the impact it can be huge, but you can't say it in general. The impact of co-simulation, for example, on simulation time depends on the time resolution of the two models. How strong is the interaction? Is it really like, for example, a control algorithm which can really have like intermittency, another system which is very slow, and depending on all those factors, it can have a tremendous impact or a negligible impact. What I do see is that we do tend to see more and more simulation platforms which are not maybe really domain specific. Like, for example, Modelica has not been developed. It's not actually a building physics platform. It's actually a modeling language with different softwares implementing it, like, for example, Daimler or Open Modelica, etc., which actually then you don't talk anymore about, like, you can put whatever you want in it. Will it happen more? I think it always has happened. If you look, for example, at studies on indoor air quality and energy use, it has been done for decades. Will we see it more? I think it's only something you do when you need to. If you don't need to, you don't make things complex and you try to have it in one tool. But I think we will always sometimes face something else, because then you suddenly want to add another field of research, because after all, we are just applied scientists. And this, yeah, I think we will always need it, but I don't know if that's an answer to your question.
No, it is, because we, at least for our students in this course, we set up a scene for showing them a co-simulation in next term. So I just wanted them to hear a bit more about that particular subject.
Thank you. Dru, I don't know if you have any comments about that when you look at the diversity of data that you're starting to bring into to some of these models.
It does tend to, and I like Marc's approach, simplifying. And Marc, one of the thoughts I had after your presentation was that the user becomes the black box portion of the modeling. That kind of stuck out to me. But I think there are going to be opportunities for the FMUs and the co-simulation in many respects, because no tool does everything. And there are tools that do better. And, you know, researchers have been looking at this, as Marc said, for decades. And how can we combine the strengths of one tool with the strengths of another and come up with a better solution? But I think for most practitioners, if you're doing EPD or you know, SAP, those are very simple models, and they're not going to see that sort of complexity. These are more research sort of topics and less day-to-day practitioner use. You know, there are practitioners out there that are able to use this, but for the most part, this is not a standard simulation problem.
Mm-hmm. Thank you. And I think, so I have a question for the panel, which I think follows on from that, which is around this, this question of the complexity in research use. You know, the development, everybody does their PhD and, you know, they have their particular problem, and they spend, I would hate to work out how many hours over the course of their PhD working on this one particular thing. And you end up with something, you know, an incremental improvement, but it is typically it is an increase in complexity. And then we have the tools that practitioners need when they're working in what's often quite a cost and time constrained environment, and how do those get brought together? I mean, we see to a certain extent we have used in this course, we've used things like Design Builder, which is a user interface which is to a certain extent allowing practitioners to interface with a complex tool like Energy Plus. But what do you see as the challenges, and where do you see that this goes, bearing in mind the issues that we've seen, and as Marc highlighted, around understanding what it is that you're putting into your model? I don't know who would like to, should we take that from a daylighting point first? Eleonora, is that all right?
Can you just repeat the point?
I think, how do you see these advances that are being made in research tools being brought into tools that are used by practitioners in a meaningful way that involves practitioners making informed decisions about their modeling, rather than risking just pressing a button and accepting the number that comes out?
Yeah, well, part of it is from education. So yeah, if the more practitioners are educated to the field of building simulation as a natural field that they need to learn, and the critique of the simulation tools. So it's not just taking for granted that what results from it is just the truth. And I think what I would have liked, I still would like to see, would be more benchmark systems. So system that people can refer to judge whether their results make any sense or not. So this is for daylight, but it's, I guess, for many other fields. So like some authority in the field, whether it's a research group or a professional association that set up a collection of data, or both simulation data and measure data, where you can look and refer to and get a feeling for what you're doing, whether you're going in the right direction at all. So I think that would be more useful for practitioners as well, rather than adding too many complexity that they don't need. And also I would refer back to what I mentioned in my presentation. Practitioners really care about regulation. So they're tied to what is asked to them in terms of complying with building regulation and all that. So that is also quite a limitation. You can do all sort of amazing simulation, but then what is asked from you is just the bare minimum. And yeah, we could do better also at providing regulation that promote better performance and better better buildings.
Yeah, thank you. Marc, do you have a comment on that?
Yeah, maybe two things. I think, Pamela, you stressed a very important distinction, is the distinction between the complexity of the algorithm as a complexity of the interface. Because I've seen many discussions, for example, in Belgium about complexity and simplification in EPBD, for example, about people saying, on the one hand side, they say we should make things dynamic instead of monthly calculation because it will solve all potential problems. On the other hand, they want to have everything very simplified. But actually in reality, when they discuss about that with them, they don't care about the complexity of the kernel. They care about the complexity of the interface. And so make always a distinction between those two, I think is very crucial. But of course, the more you simplify the interface, the more risk you have that people take things for granted, what's behind, of course. So I think that's a big question. And I fully agree actually with what Eleonora said about needing data to validate. And I think you can do it either on the one hand side by really have like validation sets. But I think, and what I hope for, is that actually it might become a part of evolutions that we see actually in whole building processes. for the moment, you have people like doing a simulation in the design stage, and then you give the key to the owner of the building, and then you say bye, and you don't see each other again. As a result, of course, a person who has done a simulation will never have the opportunity to check his or her results with measurements. And if we think about evolutions, like for example, on buildings, from an architect engineering making a design and then saying bye towards DBFM, for example, design, build, manufacture, maintain, those situations where the same group of people who were present during the design stage are also have a responsibility during the operational phase, then of course the same people end up being both at the buttons of the model, but also at the key level of the data. And then you might hope that they will notice things, and just by doing and learning. You see the same actually even at companies. You see shifts from product selling to service providing, even in ventilation and HVAC. And the moment you do that shift, of course, then the people selling a product, to be a little bit blunt, they want to be able to say, look on paper how well it works. For example, like Eleonora said, compared to regulation, if however you sell a service, your margin of gain is usually by, for example, saving more energy than what the monthly bill is for the person having that contract. Then of course you start to be really interesting in the real results of what you are doing. So my hope is actually for shifts in building and standard practice to actually link with those challenges of having people like reflect on their own project later on and seeing, damn, we made an error 3 years ago in our simulation model. Let's learn it for next one.
Yeah. Farhang, how do you think the sort of the huge role of occupants in determining energy consumption, for example, fits into that picture?
Actually, it is tricky. I agree with both all the speakers that, for example, when we teach building simulation to students, we always say, without documenting the inputs, the simulation outputs is useless. So it's always about clarifying the assumptions that you have that gives you a specific performance. And this is especially tricky in terms of the regulation that is mentioned before. Because with building simulation, you can easily get anything you want. And so sometimes maybe just get back to Eleanor about the new European standard in daylight, EN 17037. Maybe it's not, after all, that bad idea that you have a sort of still traditional method, such as daylight factor, manual calculations, but for above standard performance or for research or more advanced explorations, you have possibilities of using simulation. But specifically to get back to you, Pamela, about occupant, we really can make it more problematic, and it is happening. You know, even the use of simulation in the industry is still a challenge. Now, some of us may ask practitioners to say, yes, you need to have a stochastic occupant behavior models. That's probabilistic, that's the best in the field. So you need to repeat each simulation 100 times so that you get a more accurate things, because you have that range of error that is more accurate. And we don't gain anything, I think, from that other than making our own personal careers and pushing the boundaries of research. So I guess, again, as you mentioned, we need both research to advance the field, but also always more practical, more simple recommendation for industry. For example, again, more specifically about occupants, maybe we do everything about stochastic occupant behavior models and things like that, but at the end come with some very clear recommendation to say, if you do winter heating assessment, don't worry about any, for example, operation of windows, or if you want to capture window operation, go with this simple rule, but always document what assumptions you have made in this regard.
Thank you. And Dru, in terms of digital twins and the idea of, I guess, of heating and ventilation as a service, is there a link there?
Not so clear a link, just because of the scale, I think. But I do want to build on what Eleonora, Marc, and Farhang have said. And I think that there's a challenge within interfaces to the more complex tools, that the developer brings their own biases about workflows and paths, and that can influence what's going on more than something that's somewhat more transparent and open, but more complex. It's always important to be able to expose what's going on behind the calculations, and that I think is really critical as well.
Thank you. And I wonder from our students' perspective, so those who are the MSc students who've been with Cheng and myself and Ivan this term, how does this make you feel about the challenges that you faced in the simple models that you've been doing? Does one of you want to comment there? I might have to pick one of you if you if nobody steps up. So I am going to pick somebody. I'll be really mean. So Chad, we were recently having a conversation about some of your modelling, yeah, and your comparisons between these two individual, these two different approaches, actually using the same simulation engine behind them, and the challenges, even with the simple model, of having exactly comparable results. And the reality is, you cannot produce, these two tools, these two approaches do not produce exactly comparable results, precisely because of some of the interface issues. How does that make you feel in terms of how confident you would feel about going into practice after this using these tools?
Well, not very confident right now until I have a better understanding of the tools, because where I'm so new to the tools, I don't know if the difference in results is based on the tools themselves or if it's based on input error, because I don't know what I'm doing some of the time. Yeah,
but I think one of the really important things here is that that questioning approach that you have learned to take to that, and in particular to, even when you know these tools very well. And I don't know if perhaps some of the panel might like to comment on this, but as experienced practitioners, the danger of assuming that because you know what you're doing, the number that pops out once you've put your input values in and run your simulation is the right number, or is it just a number until you've questioned it and interrogated it? Would you like to share your experiences of that? I'll start, actually, I'll ask someone who's not on the panel. Ivan, do you want to comment? What are your experiences of producing numbers that you think might be right and then you later find are not right?
I never trust them. So I never trust my numbers. So I always, I've been using a lot Energy Plus in the past, and now more recently combining Energy Plus and Daimler Modelica, so co-simulation and stuff like that. My nightmare is to assure myself that model really does what I'm expecting it should do. And I probably can claim that I spend almost equal amount of time checking all possible outputs, nodes, flow rates, temperatures, just to try to spot is there any misbehavior in the results that I can spot through visual observation or writing some small script to try to identify misbehavior, something which should not be there based on what I'm expecting of the model behavior. But that takes a lot of time and also requires knowledge about first fundamental building physics or building services systems, performance, operation, control logic, control sequences and stuff like that. So it requires a lot of specialist knowledge. And my general message to students on courses like this one is that knowing the fundamentals, it's very important, because that can massively help debugging, because starting creating model from a blank piece of paper, it is prone for errors, for just mistakes. And knowing the physics behind fundamentals, it is very, very helpful. So focus should be on understanding background behind the model, and then searching, checking the results as much time as possible. So within the certain time scale, try to assure yourself that model behaves in the way it should. So that's from my personal experience. But again, that was mainly in the research context. When I worked in industry, I never had time to to invest in proving a model to the level I am fully confident that it is fully operable, fully working.
Yeah,
Eleonora. That's also what getting a PhD does to you.
Yes, probably.
Yes, there was a little question in the back of my head there, which was, is there another IEA annex, which is about, I don't know, kind of tools for practitioners, you know, a little bit like Eleonora, your benchmarking point, but whether it's just, you know, workflows that people would use to error check things that ought to be the kind of standard, because people tend to do this based on experience, and that might be, certainly in my case, it was bad experience. It was presenting something and then someone asking me a question and not being able to justify why the model did what it did, which was very embarrassing, and certainly focused my mind on the need to properly understand what was happening. Which is challenging, I think, even in the context of a PhD. You can be still very time pressured to produce results. It's tempting to accept the answer that you've got and to move on and do something with that answer. It certainly is the case in industry. So I don't know, maybe there's another annex there. Marc, you are into, how many annexes have you worked on now?
Currently only 2. But the big issue, of course, with checking if a model is doing what you expect to do is the issue. You can only check it once the real life case is there. So you cannot check in advance if a model is correct. And of course, you can check whether a component is correct. For example, your boiler component or your wall components, if you do a thermal simulation. But if the whole model of your building is correct, well, unless you wait for the building to be constructed and in use, you don't know actually. And that's something we just have to live with. It sounds a little bit maybe I don't know, like disturbing. Yeah. But also I'm sometimes wondering is how detailed do we need those models to be? That's one thing. Do we actually really need to be able to model to 1 degree accurate what will be the temperature inside that room when outdoors it's that temperature, because actually it will never be that temperature outdoors, but they have the same inhabitants. So do we need, how accurate does it need to be? So that's maybe a second question I'm always wondering. And the last thing is also the checking of phenomena. I'm quite amazed, and I've never been that long in practice and never with simulation, so there's my experience there is in research. But talking, for example, to people I've studied with who are in practice, I'm always amazed at how many wrong things are told, which you can like make visible after just 2 questions. Like, for example, predicted savings, energy savings and costs, which are communicated. And then you can do a very simple calculation with like average outdoor temperature, average indoor temperature, that many months a year, it's delta T with that U value. Is it even reasonable what people are telling me? Or just saying you insulate your roof, you might save that many energy. And then you just look, well, the roof is only that much percentage of my whole envelope. And just by that kind of very simple things, like half of the things communicated in practice about savings can be like corrected just by that kind of very logical reasoning. And I think that the main issue is a computer is just a computer doing what you are telling them to do. Computer is never clever. And I mean, you're the designer. Use your logic. And of course, that's the only thing we can do. And that's a fun thing about designing. If designing was just about programming codes, which I like both, that would make design like tremendously boring, even though I think programming is tremendously great.
Thank you. Eleonora, did you want to comment on that?
I don't find programming boring, but that's another thing.
Yeah.
I love it.
Yeah. No, it just on the other side, on the measurement side, as in simulation, we take measurement as a ground truth, but especially if you get data from sources that, if there are data sets that you didn't measure yourself, how much then you should also trust those data, and what uncertainty can you apply to that? Can you label those data with? Yeah, like where the sensor were positioned, or I don't know, so many things.
Definitely. I think I also have a little bit of a bugbear with calibration, a kind of manual calibration exercise that sometimes is undertaken that involves effectively tuning a model to produce the same outputs as the data that has been collected. Typically involves adjusting a tiny proportion of the overall set of inputs, and it is not clear that you have adjusted the right set of inputs necessarily. You may have adjusted the most obvious set of inputs, but there may be other sets of inputs which you could also adjust, which would achieve the same output. And so you do, how do you know that model that is calibrated is right, unless you have looked at the sensitivity of your model overall as part of that exercise. So I think, but it comes back to this point, which I think for for Chad and for the other students is, it feels like self-doubt. Do I know what I'm doing? Did I get this right? As though that is a thing that should go away, when in practice that shouldn't go away. You should retain that questioning mindset throughout. And the problems come when you place too much reliance on the output that you get from that model. That they're really helpful tools if you are questioning and checking and understanding the limits of the inference that you make with that model, but not if you are if you just push information into the model and accept what comes out without questioning.
Yeah, that's small.
Of course. I think Dru as well.
Go ahead, Marc.
Go ahead.
I was just going to add that I'm less interested in a number that comes out than I am in the sensitivity. If I'm making a change in the building fabric thermal properties, am I seeing a reasonable number, a change there? And then I'm beginning to get the feel for how the model is working, rather than it's an absolute so many kilowatt hours a square meter.
Thank you. Marc, sorry.
What I think is a very relevant point you were addressing, Pamela, by stating like you don't know when you are like calibrating whether you're like tweaking the correct parameter, which is really the culprit or not of the error. But I think we often also tend to forget to first look at, do we actually care? Depending on the application, sometimes it's very important to tweak the correct parameter, but strangely enough, sometimes you don't care whether you tweak the correct parameter. It might sound blunt, but if, for example, the idea of the model is to compare different potential scenarios, like should I insulate more the roof or the wall, then of course you don't want to have corrected the U value of the wall, while it should have been the U value of the roof that was wrong, because otherwise your different scenario will be biased. If, however, your model is not aimed to do that kind of scenario analysis, but your model is, for example, aimed to be used, I'm just saying, for that existing building in that existing status, for example, some kind of predictive control, sometimes the only thing that actually matters is whether the output matches well enough with what happens. And it's like a little bit like with regression analysis. It's very similar. All discussions, many papers that just do, for example, linear regression modeling of whatsoever, tend to really do very, very bad regression diagnostics. But on the other hand, sometimes people are blindly staring at multicollinearity, seeing, well, this parameter is correlated with that one, and I don't know which one it is. Well, if the data set you're going to apply your model on is almost identical to the training data set, and there also that correlation exists, then it might not be a problem actually that you don't know which parameter should have been tweaked, because the model will give the same prediction, and if you only invest in the prediction, you don't care. I don't know if it's clear what I'm saying, but depending on the application of the model, the requirements you are imposing to the model will be different. Depending whether you really want to know the properties of the components, or do you just want to have a correct prediction for example, tomorrow. And then you can really change your approach in calibration, but also change your requirements and stuff.
Thank you. So I guess if I was summing that up, I would say that we've got these pieces of advice. One is always doubt yourself and check. Another is about understanding, using sensitivity to understand how your model is behaving. So not just the actual number, but looking at directions of change and magnitudes of change, if those are what you expect. Another one is thinking about the application case that you're working on here. Is this the right, what do I need to know in order to do this? I think Farhang, you began with the fitness for purpose, fit for purpose, modeling, and the most appropriate model for what it is that you are trying to do, and that simpler models, as Marc has said, can be better. Is there any last piece of advice that you would leave the students with?
I would add to your list, as I mentioned, documentation of inputs. It would be great if students are getting used to the fact that it's not just about the performance metric that you show, but you need to always communicate at least the key inputs that you have set. That shows your awareness of the thing and also allows your client, your lecturer, to evaluate your performance. Yeah. And
adds to Eleonora's point, of course, about not all inputs are equally certain, and understanding your confidence in that. Thank you. I think we have run out of time. Is there anybody who has any burning question that they just have to have answered right now? If not, then I would like to say thank you very much to the panel. That has been a really, really interesting discussion for me. I hope that everybody, I hope the panel members enjoyed that and found that an interesting discussion. And I hope from the students' perspective that was informative, but also inspirational, looking at the directions that you can go in from a starting point in building simulation. So thank you very much. And I wish you all very happy holidays and happy assignment completion for the students. So thanks, everyone.
Thank you, Pamela.
Thank you. Thank you very much for inviting.
It was interesting.
Bye.
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 You really do too.